Welcome to this module, and in our last module what we have seen? We have seen how we can fabricate an interdigitated electrodes over an insulator, and below the insulator there was a micro heater. The idea of learning this particular topic is to understand how we can fabricate devices or chips for biomedical applications, in particular to understand cancer, and rather than understanding cancer, to diagnose cancer at an early stage. So, can we add modalities other than optical modality or biomarkers? So, that is what we have discussed last time, that if you take a tissue from a breast, right, it is a breast cancer, then generally how it is identified, that a woman has to go to a hospital where MRI or mammography is performed, and then if the area is suspicious, then the tissue is taken out from the suspicious region and is sent to the path lab, where they understand the biomarkers present in the tissue. What are those biomarkers? We discussed about those markers. They were HNE, prostrogen, estrogen, HER, P63, SMA. These are several biomarkers. Now, in particular breast cancer, there is something or subdivision of breast cancer which is called triple negative breast cancer, and in that none of these biomarkers are present. Then how we can identify there is a cancer or not? Or even if their biomarkers are present in other subdivisions, there are false positive and false negative signals. So, how we can reduce those false positive and false negative signals? By taking the help of engineering. So, the idea here is that we will understand a mechanical property, a electrical property and thermal property of a tissue. That means, we are adding 3 different modalities to the existing modality, and we are creating a biochip that can aid a physician to take a correct decision, right. So, for that correct decision, this device or the chip should be able to measure electrical, mechanical and thermal property. So, in our last modules we have been understanding how we can fabricate this particular biochip, and we talked about biochip. We also talked about heater, how we can design a process flow, right, to pattern a heater made up of either nichrome, nickel, platinum, chrome gold, right. And once you have a heater, you wanted to have a interdigitated electrodes, but you cannot have metal on metal, and that is why there should be an insulating material over which there were interdigitated electrodes, and that was what we have seen in the last module, how we can design or pattern interdigitated electrodes on insulator, right. So, if you see the screen, what we discussed last time, it was interdigitated electrodes, right, over an insulator, and below the insulator there is a micro heater. So, until now we have seen how we can design a process flow for fabricating a micro heater. Then we have seen how we can pattern interdigitated electrodes on an insulator. Over this there is an insulator, on which there are this interdigitated electrodes, right. And then we also seen that we have to open this area, we have to create a window to open this area, right, and remove the insulator from that particular area, so that we can have a external contact. You can see here contact pads for the micro heater. On this chip, next step is we want to have a piezoresistive material. We want to have the piezoresistive material. So, how to pattern this piezoresistive material, right? How to first deposit and then pattern this piezoresistive material. So, we can use several piezoresistive material including silicon, you can make a piezoresistor with a polysilicon, right, and or we can use a conducting polymer called P dot PSS, So, if you remember the last screen that we have seen, right, which is our interdigitated electrodes, this one, right, and below interdigitated electrodes there is an insulator, below which there is a micro heater. So, we will start from here and then we will pattern a piezoresistive material, right. So, I had to draw that particular schematic diagram to start from this particular end, right, and then we will see from here how can we reach to this particular chip. So, this chip, let us say I give A, B and C. So, we are drawing B, okay, cross section of B. So, I have insulator which is my oxidized silicon substrate, on which I have my micro heater, on which there is an insulator, right. So, let us say this is an insulator, these are the contacts, right, contact pads to micro heater. This is your micro heater, right, micro heater. This is SiO2, silicon, SiO2. Right. On this there were interdigitated electrodes, right. This is what we have seen. So, I will draw interdigitated electrodes in terms of like dots to just distinguish from the heater, all right. So, this is my interdigitated electrodes. So, what is the next step? Next step is to spin coat a material which is my P dot PSS, right. I will spin coat P dot PSS on the entire wafer, right. What is P dot PSS? P dot PSS is conducting polymer and it can also act as a piezoresistor. Instead of P dot PSS, I can use any other piezoresistive material and deposit it, right. So, this is nothing but piezoresistive material. Property of piezoresistive material is when you apply pressure there will be change in resistance, right. So, piezoresistive material. On this piezoresistive material, what is the next step? After I deposit piezoresistive material on interdigitated electrodes, I had to go for lithography, right. So, first step is I will spin coat photoresist, right. I will spin coat photoresist on this piezoresistive material, right. This is my photoresist. Let us say I am using positive photoresist. What is the next step? I want to create this particular chip, you see here, right. Next step is after this we all know we have to soft bake it, right. After soft baking, so soft baking can be done at 90 degree, 1 minute on hot plate. After soft baking, I am coming back to this particular schematic. After soft baking, we have to load the mask, such that I can save my material, piezoresistive material on the interdigitated electrodes, right. I am just drawing cross section for one, that is why I am drawing this particular schematic, where you can see that the piezoresistive material, right, is on this interdigitated electrode. What is this mask? This mask is my bright field mask, right. Next step is we have to do UV exposure, we have to perform a UV exposure, right. After this, next step, so we go this way, right, and we come here. After UV exposure, you will unload the mask and then you will perform photoresist developing, or you will dip the wafer in photoresist developer. After photoresist developer, what is the next step? After photoresist developer, you will see that the wafer will look like the one that I am drawing on your screen, right. So, whenever I am drawing, you can also draw on your notebook and try to see whether you guys understand how to draw it or not, right. See what I said, we have interdigital electrodes on which we have a piezoresistive material, and on piezoresistive material we have spin coated photoresist which is positive photoresist. We have done soft baking, then we have loaded mask which is bright field mask, we perform UV exposure. After UV exposure, you unload the mask and perform photoresist developing. After photoresist developing, what we get is what we are drawing over here, right. So, you guys can also draw along with me, right, and then let us see whether both of us are drawing a similar thing, so that we understand that you as well as me, we both are drawing things that is similar, and that should be correct, right. And if that is not correct, you can always improve. So, photoresist developer, then we have on the photoresist developer we have interdigitated. After photoresist developer, how the schematic will look like? Schematic will look like the one that I am drawing on this particular screen. So, after this piezoresistive, and so this is my photoresist, this is my piezoresistive material, right, this one. Then this one is interdigitated electrodes, then this one is micro heater, this we already know, SiO2, silicon, SiO2, right. Next step, what is the next step? After photoresist developer, next step is post bake. Post bake is done at 120, 1 minute on hot plate. After post baking, what is the next step? After post baking, the next step would be to develop or to etch piezoresistive material from the area or from the unwanted areas. We only want piezoresistive material on these electrodes, we do not want on any other side of the chip, correct. So, that is why we have used photoresist, and we have patterned the photoresist in a way that it will protect the piezoresistive material below it only in the wanted area, and the unwanted area you can see that if I put this chip in a piezoresistive etchant, right, whatever the material that we are using, the etchant for piezoresistive material, what will happen? That the piezoresistive material will get developed or will get etched, right. So, you see this area it got etched, rest of the area it got etched, correct, right, easy. After this, what is the next step? We have to dip this wafer, in acetone. Why? Because we do not want photoresist, we have to strip off the photoresist. So, if I dip this wafer in acetone, what will I have? I will have piezoresistive material on my interdigitated electrodes, right. So, if you see the entire structure, silicon oxide. So, we can say oxidized silicon, on that there is a micro heater on which there is an insulator, the contact pads of the micro heater are opened, on which there are interdigitated electrodes, on which there is a piezoresistive material. Easy. Now, what is the next step? Next step is that we have to have a gold pad, this particular chip, right. We have to use this particular chip. What is this chip? You see, let me just use this design right over here, so that we know what is the next step, right. Our last step was that we created piezoresistive material on interdigitated electrodes, right. Now, our next step is that we want to have a gold pad with SU 8 pillars. This is, if you see this one, right, this is your gold pad with SU 8 pillars, gold pad with SU 8 pillars, right. I will tell you what is the role of each material. You should also start guessing it, right. It is a heater for thermal conductivity of tissue, piezoresistive material for understanding stiffness of tissue, electrode for understanding resistance of the tissue. So, we will see how we can use this biochip. Right now, we are on this stage. From here, first step is we have to create a gold pad. To create a gold pad, if gold if I deposit gold directly on this particular chip, which is, let us say this is A and this is B. If I directly deposit gold pad on A, then there will be short between piezoresistive material and metal, and that is why the next step after A should be that we have to have an insulating material. We have to have insulating material. So, what does it mean? That we had a oxidized silicon wafer on which there was a micro heater, on which there was insulator, correct, on which there were interdigitated electrodes, on this there was piezoresistive material, right. So, if I just draw it to just make sure that we both, you guys and me, we are on the same page. What is this? This is your SiO2, this is silicon, this is SiO2. Then what is this one? This is again SiO2, right, insulator here insulator. Then what is this one? This is our micro heater. Then what is this one? This is your interdigitated electrodes. What is this one? This is your piezoresistive material, correct. This is your A, and next is we have to deposit gold, but like I said, we cannot deposit metal on piezoresistor. So, what is the next step? Next step is we will deposit and pattern insulating material on the chip. Next step after this, the next step would be we have to deposit gold. What is this material? SiO2. SiO2. What is this material? This is gold. I already told you that some metals cannot be deposited directly on the chip. The reason is that these metals, they have poor adhesion to the substrate, and to improve the adhesion we have to use a combination of another metal. In case of gold, gold has poor adhesion to oxidized silicon, and that is why we have to use a thin layer of chrome along with gold. alright. That is why we always write chrome gold, but the thickness of chrome is extremely thin compared to thickness of gold, alright. So, what is the next step after this chrome gold? After chrome gold we have to create a pad. For creating a pad, the next step would be we have to. So, what is this one? This is your chrome gold, right. After this, next step is photoresist, right. Now, after photoresist you already know what is the process, photoresist, then we have to soft bake. After soft baking you have to load mask. How the mask will look like? Mask will look like something that I am drawing right over here, right. Mask will save my gold pad on the piezoresistive material, right. It will be directly on pattern on the same area where there are piezoresistive sensors. But the one thing that we have to remember is that below the metal, below the gold pad, there is an insulating material, alright. You can see chrome gold is there, insulator is there, below insulator there are interdigital electrodes, and below above interdigital electrodes here this is piezoresistive material, okay. So, this is my mask. After my mask I will perform UV exposure. After UV exposure you know what is next step, photoresist developer. After photoresist developer, what is the next step? After photoresist developer, the next step is that post or hard bake. Post bake or hard bake is done at 120 degree 1 minute on hot plate, right. Post bake or hard bake 120 degree 1 minute on a hot plate. After post bake, what is the next step? Next step would be I will etch chrome gold from the unwanted region. And what is unwanted region? Unwanted region would be, so if I complete this many steps, how my wafer will look like? So, I will draw it right over here. My wafer will look like what I have drawn right over here, right. And so, let us draw on the next slide. So, it is easy, right. I will draw two schematics here and you see what is the difference, okay. What is the difference? For first schematic should be an oxidized silicon substrate on which there is a micro heater. So, let us draw micro heater. On micro heater there is an insulator. We all know, we are discussing this from 2-3 modules. Right. On insulator, so insulator we can draw similar, which is silicon dioxide. There are interdigitated electrodes. Correct. On this there is a piezoresistive material. On piezoresistive material we have silicon dioxide. On silicon dioxide we have chrome gold. chrome gold. On chrome gold, after we perform the lithography step on chrome gold, we can pattern the photoresist in this particular fashion. This is your photoresist, all right. And if I dip this wafer, so if I write down SiO2, silicon, SiO2, micro heater is nichrome, then SiO2, then interdigital electrodes, then piezoresistive material, then SiO2, SiO2, right, on which there is a chrome gold, on which there is photoresist. So, if I dip this wafer in a photoresist in a chrome gold etchant, first I can dip in gold etchant followed by chrome etchant, right. What will I have? I will have correct. I will have chrome gold in this particular fashion. If I etch chrome and gold, right, from the unwanted area which is not protected by my photoresist, right, chrome and gold will be etched from this region, right, and what will I have? I will have a chrome gold pad. Now, this is just a schematic to show it to you, right. You can also have photoresist in this particular fashion, so that your pads below the photoresist will not get etched. This should not get etched, right. This one and this one, they are directly exposed, and they are also interdigital electrodes which are made up of chrome gold. So, chrome gold can get etched if this is not protected with the help of photoresist. So, you can draw a schematic which is similar to schematic 1, right. And when you perform lithography, you can save the area with a photoresist, or you can mask the area with the help of photoresist. So, that when you dip the wafer in chrome and gold etchant, the chrome and gold will get etched only in the region which is not protected by photoresist, right. And the region which is protected by photoresist, you can see here, you can save the region which was protected by photoresist. This is your photoresist, right. This is your chrome gold, and chrome gold, over chrome gold there is a photoresist right over here, and probably right over here, right. Or you can just say that you have a thicker electrode, which is even better, thicker electrode, because you are depositing chrome gold every time, you have thicker electrodes, and on thicker electrodes you have your photoresist, right. Now, what is the next step? Next step is that you have to strip photoresist by dipping the wafer in acetone. We all know, by dipping the wafer in acetone. If you do that, what will happen? The photoresist will get stripped, and you will have a chip with a gold pad on interdigitated electrodes. So, what we will have? We will have this particular chip, but without SU8 pillars, okay. So, if you perform this process flow, what you are getting? You are getting a gold pad, this circular gold pad you can see right over here, which is connected here and here, right. And this gold pad, below this gold pad there is a insulating material which is SiO2, below insulating material there is a piezoresistive material, below piezoresistive material there are interdigitated electrodes, below interdigitated electrodes there is another insulating material, below that insulating material there is a micro heater, correct. So, what is the next step? Next step is that we have to now pattern SU8 to form this particular structure which are like a pillars of SU8, right. So, how we can do that? How we can do that after this particular step, how we can make SU8 pillars or how we can pattern SU8 to form pillars. This we will see in the next module. Till then you just look at whatever we have done here, understand. See, I am going little bit slow so that you guys do not get confused. Once you understand a process correctly, it becomes really easy, but the chip that we are designing is really complex. If you now have noticed that we started with just a heater and then we have an insulating material over which we have interdigital electrodes, over which there was a piezoresistive material, over which another insulating material, on that there was gold pad, on this now we are looking at SU8 pillars, and then SU8 is polymer which is non-conductive polymer. So, we had to make it conductive because SU8 pillars along with gold pad will act as a one single electrode. How to do that? That is the next step. Once you do that, you have to perform front to back lithography to create a diaphragm, and then you have to use this chip inside a tool so that you can measure the properties of a tissue. So, it is complex, but it is not so difficult that nobody can do it. Everyone, you guys can do it once you understand process flow. You understand process flow, you understand recipe, you can design any sensor. So, let us talk about how we can spin coat SU8, and SU8 is nothing but negative photoresist. Now, you all remember, right, what is the characteristic of positive and negative photoresist? Positive photoresist, the unexposed area will be stronger. Negative photoresist, the unexposed area would be weaker. SU8 is negative photoresist. So, if I want to create SU8 pillars, I have to be smart to understand what kind of mask I have to use, so that I will have the pattern on gold which are my SU8 pillars. And then in this we will see a very interesting technique called lift off technique to make this SU8 pillar conductive, right. Till then you just go through this lecture and I will see you in next module. Bye.